Swayam Prabha. Digital India. Educated India.
Good morning, welcome you all to the next lecture in this particular course on analytical, spectral and microscopy applications of inorganic compounds and nanomaterials. Essentially we will be continuing with the previous class, which previous two classes in fact, wherein I have treated with the magnetic aspects. In those two classes I have given the very basic aspects of magnetism in terms of diamagnetic, paramagnetic, ferromagnetic, ferrimagnetic, antiferromagnetic, etc. The way that these are understood, the susceptibility graphs as a function of temperature, or inverse susceptibility graphs for the temperature, etc. So we also looked at how physically one can visualize all of these, and then we have looked at the representing the susceptibility is a very difficult because it is a 10 power term. So it's easier one is to look at the magnetic moments. So therefore we have looked at the magnetic moment aspects of it. Then we came up to the magnetic component when you look at the inorganic complexes or any of the transition or inner transition complexes. So what you will have a component from the spin, you also have a component from the angular part of it, okay, orbital part of it. So we have looked at which kind of a configurations are capable of giving these orbital angular momentum contribution that we have looked at. In some cases where the normal conditions will not favor, but the excitation may favor, excited state populations may favor, that also we have looked at. So in effect we have looked at the different kinds of spin states that are possible for a transition metal under a weak field, under a strong field kind of a conditions. Then we also looked at the low spin to the high spin, because whenever you have a strong field then you will have a low spin, whenever you have a weak field you will have a high spin for the same given ion in inorganic complexes. So that means you can switch over the spin basically from low to high or high to low, and that is what is spin crossover we have looked at. And the spin crossover has an influence in having applications, the one which you routinely see for these swiping cards, etc. Then we looked at another important aspect when you have two paramagnets connected in a molecule, even in single molecule through different ligands as a bridging between them. Now how these two vectors will orient, so they can orient in the same direction, give ferromagnetic coupling, or they can orient in opposite and give a antiferromagnetic coupling. It all depends upon the orbital overlap, orbital orientation of these spins. So therefore that means the two magnets that we are referring to, the connectivity between these two, that means the angle between these two will basically decide, because these bondings are through the overlap of the orbital from the ligand and orbital from the metal ion. So that is how you have. So therefore this angle will favor in some cases ferromagnetic coupling, in the other antiferromagnetic coupling, depending upon the orientation of these things. So as a result of that, that means we can try to adjust these angles by putting these molecules onto some kind of a surfaces, like for example we looked at an example of the carbon nanotubes where they have some curvature. So this curvature can be adjusted by adjusting your diameter or the radius of the tube. So the smaller the one, the greater the curvature, the greater the one you have, a smaller the curvature. So therefore the bending of your molecule on the surface would definitely reflect on the corresponding antiferromagnetic or ferromagnetic coupling aspects of it, because the angle between the two vectors do change. So I think at this stage we have come to the level where we need to look at these ferromagnets, how one can do the magnetization or magnetic materials doing the magnetizations. Draw your attention to this particular slide. So, you can see in the normal state you have spins because this is the ferromagnet. So, you have a zones, you have a zone here, another zone, another here. So, where the spins are all oriented. So, this whole zone may have some compensation with this, that is how you have, but net you have a ferromagnetic. Now, such a ferromagnetic thing, if you put under the magnetic field and keep changing the magnetic field, you can try to. So, when you reorient, you may be able to merge different of these zones. So, for example, here you can see this zone and this zone got merged, and as you keep further putting under the magnetic field, you can see more or less you can make. So, that is how you can do the magnetization aspects. And now what do you, this is a physical way of looking at it. The measurement, if you look at, so what you are doing, there are two parameters. One is you are applying a magnetic field, other is you are measuring the magnetization. So, the magnetization is referred in some cases as a B, in some cases as a M, it does not matter, one and the same. So, the magnetization is on the y axis. Please keep looking at the slide. Magnetization in the y axis and the magnetic field applied is in the x axis. So, the H and the B, you can see you start from the no magnet or no magnetic field, and then you keep please follow this cursor. So, the magnetic field as you keep increasing, so that increases, and at its stage it gets saturated, okay, and that means there is no further change in the magnetization. You cannot do any more magnetization. That means there is a certain level of magnetization, because when you do the magnetization, there is some resistance also from the material not to obey the rule of the magnetic field. Then when you reverse back the current flow in this, then you can see the magnetization slowly dropping down and then going through that. Again, there is another level of saturation is there. Now again you reverse back, so you can get, so this is whole one cycle of the loop, and this the path when you reverse back does not go back into this. So, this kind of a situation when it does not go by the same, and this kind of things are referred as the hysteresis. So, here this is a magnetic hysteresis. So, a very important concept, because this is the one which stores the magnetic energy. So, magnetic hysteresis. Okay. So, this magnetic hysteresis is nothing but the one which stores the magnetization, magnetic energy, if you want to call it, magnetic force, that particular zone is trying to hold, that particular magnet is going to hold. So, that is what it is. So, that is a really important parameter, because this can be used for application part of it. Keep looking at the slide please, and see that I have shown on this right, there are two levels, one is with the blue loop and the other one is the red loop. So, obviously we can see the blue loop has got a huge amount of magnetic hysteresis, and the red loop has got a very small amount of that. And this is what refers to the hard, the greater the magnetization is a hard magnet, and the smaller the magnetization is the softer. This is not because you have not magnetized enough time. No, this is not because of that. It is because of the nature of the material. So, the nature of the material in the red allows only this much. The nature of the material that we have used for the blue uses that. If you have not applied sufficient amount of magnetic field, that is not correct. Okay. So, applying the same level of magnetic field, still you get lower level of hysteresis, a greater level of hysteresis leading to the hard and soft magnets, and these are basically used in variety of applications. If you just Google, you will find a huge number of things. So, these are hard ones are basically referred as the permanent magnets, and the soft ones can be easily erased and then reworked out. So, this is AlNiCOS is should be read as Al as aluminum, Ni as nickel, Co as cobalt, S is sulfur, and that is how these things. SmCO, that is samarium cobalt type, neodymium iron boron type. These are all variety of magnetic composites wherein the magnetizations will last for long, therefore, they are hard magnets. In many of the instruments where the magnetizations require, for example, nuclear magnetic resonance and electron paramagnetic resonance, which we are going to study in this particular course, the later stage, they all require a huge magnets, magnetic power. Soft ferromagnets, these are used in transformers. These are from iron silicon alloys, amorphous, nanocrystalline, and alloys, nickel, iron. So, a variety of AC applications as well as DC applications you can use. This is another concept that I have introduced to you now, which is very important for their application aspects of it. I said earlier, when you try to apply a magnetic field, it does not mean that the material has to get it has to listen to the magnetic field and then get oriented. No, the material can say, no, I am not ready to orient to the magnetic field. So, that is means that is to what extent can you do the magnetization. Okay. So, that is where. So, for example, if you take oxygen, so you know the oxygen molecule has got two unpaired electrons. So, therefore, it is a paramagnetic that you study in your 12th standard by using the molecular orbital theory, and then you see two of the electrons are unpaired, and then therefore it is paramagnetic, and in the N2 all are paired, and therefore it is diamagnetic. You studied already. Now, so if you take let us take an example of the oxygen. Take 1 kilogram of oxygen, and let us say it is subjected to a very strong magnetic field such as 20 into 10 power 6 amperes per meter. Okay. So, that level of magnetization you are applying. So, we would like to find out what is the level of percent of magnetization. If it listens to it, then it should become 100%, it will not be, you can see that. So, if you have the magnetization for this in the regular sense, so O2 has got two unpaired electrons, that means N is equal to 2, therefore mu effective or spin only in this case is the square root of 2 into 2 plus 4. So, that is the square root of 8, that is 2.85 or so more magnetons. So, this is the level of magnetization in terms of magnetic moment you expect for this. So, now you can see this number of molecules that are there in the per kg weight. So, that we know from the mole Avogadro number 6 into 10 power 23 and then 32 grams. So, therefore, divide by with that 0.032, then you will get the number of molecules. Now, you know one molecule have got this. So, therefore, total so the magnetizations can be worked out, and that is coming to be around 497 m square per kg of that. So, now, but if you look at the actual measured magnetization under this field, and that has given 27.2. So, 27 over 497 into 100 is around 5.5. So, that means only 5.5% of the molecules have listened to the force that you put, magnetic force. So, that means it is not true in all the cases. Those which really align to them, they are the ones which will become the strong hard magnets, and those which will not listen to them will not become that, and those which are intermediate can become the soft. So, that is how the extent of magnetization into this material. So, you can magnetize and keep it. Now, you can use the magnetic cores in many of the applications. For example, Fe3O4 is a very nice magnetic material you can use. Nowadays, with the nano chemistry methods, you have a lot of the synthetic skills to make these magnetic cores. An Fe3O4 core, for example, you can see that, and then this can be covered with some silica, because there you are going to put some other things here. For example, this amino propyl triethoxysilane is put, therefore amino groups are coming up. That means you can make the surface to positive by putting carboxylic, you can make the surface negative, etc. With this, are you going to tamper the magnetization aspects of this? That you can see. For example, here it is a particle size. If you take the just simple iron 3 Fe3O4 core, you have a very fine distribution with about 10 nanometer size, but when you put it a core shell with a shell is by the silica, then the particle sizes will increase into 50 to 60 nanometers. Now, if you look at the magnetization curve, this is a magnetization curve, and this one is for the Fe3O4. The red one is for the, kindly see the slide showing that red one is the magnetization for the Fe3O4, and the blue with the star type for the Fe3O4 with the silica, and the triangle one with the silica, which is covered with this 3 amino propyl siloxane thing with the amine groups pointing outside. So, you can see the magnetization laws are not as much. So, that means you can use such kind of a cores for variety of applications, still maintaining the magnetization properties intact. That is what the basically is. Let us move to the next in that. So, we have seen earlier that you have a the soft magnet, hard magnet. So, can we make, we also have seen just a while ago about the core shell. Now, can we have such kind of a soft core shell and a hard core shell, and then join them together? What kind of a magnetization properties would come out of that? So, for example, here you have the hard inside and the soft cover outside. Here you have the soft inside and the hard cover outside. Now, these are two different core shell materials. Suppose if you can, so what you are doing is basically hard and soft, or soft and hard kind of thing. So, if you have seen already, as the soft one will give the magnetization with a small lower level of hysteresis, and the hard magnet will give you the level with a greater level of hysteresis. So, you see, if you combine them, they can join together this way. They can also join together like a two step, so which is the some kind of a two joints, two things are joined together by some kind of spring. So, that is what is called the spring magnet, and this is completely coupled. So, exchange kind of a magnet. So, here you are merging both of them and giving a new, and here you are connecting them together and giving another new, but it is spring magnet. So, such kind of a the new type of a magnetic materials will be of a great advantage in variety of applications. So, we will have some examples. So, we will see those things. For example, we are talking about the spring magnet now. So, you can see here you have two levels of things, the one with the purple, the one with the yellow, the two levels of these ones you have. So, you have a hard core with the inside and the soft core with the outside of this. So, that kind of a thing, if you look at very microscopic way, kindly look at the slide, and you can see this is what you mean. There is no spring kept by us. So, just shown to give a feel that there is a kind of an action between the one or the kind of a core shell with the other kinds of the core, that is one hard to soft or soft to hard, which is connected like a spring type. So, that means you have the magnetic information exchange. So, this core shell nanoparticle with an exchange coupled magnetism. So, now this we have the COFe209 that you can see that this is the main magnetization that you can see. These magnetization curves are done at 5 Kelvin temperature with varying the fields, etc. And then you have the MnFe2O4 which is put in the interior, and that has a magnetization curve like this dashed one. Now, you join them together, and this is what the red, you can see that you are forming a new kind of a magnetization curve. So, this is basically exchange coupled. So, you have a hard and the soft where you have an exchange, and this is a physically it is represented as spring, but there are no springs kept inside. It's a basically both the materials communicating the magnetic information. Exchange coupled magnetic nanoparticles. This way, this will have a very great advantage in transferring the heat energy, so that heat energy can be used for some application. Okay. So, let us look at the same particles have been used in this particular example, the same magnetic nanoparticles which are used to create efficient heat induction, induce heat. Because of the magnetization exchange between the two, there is a huge level of heat being generated. That heat is used for the cancer therapy. So, this is the mice. This mice is injected to have the specific kind of a cancer, so genetically made, and therefore, you have a tumor is being generated, and you have your magnetic induction coils here, and this is being placed here, and the studies were done. Studies were done at 2 stages before treating with these nanoparticles, and after you treat 18 days after that treating. So, they are all in the bottom, these are all in the top. So, you can see that. So, if you do not use these nanoparticles at all, and the tumor of course is very much. Now, when you use this core shell nanoparticle, the tumor is almost there, of course is there, and then you can see a little different way it looks, but it is there. And then if you use, this is with one kind of a material which is the iron based material, this ferridix hypothermia. So these are the ones. So this is basically the one which provides the iron micronutrient kind of thing, and not a real drug, and this is a drug, doxorubicin. Now after 18 days you can see if it is not treated with the core magnetic nanoparticles, kind of a thing is growing, a huge amount of the cancer thing blob you can see. And when you look at the core shell where you are treated with the nanoparticle, it's almost gone, kind of thing. So that itself will tell you the cancer cells were killed completely in this. Now this is a nutrient. Obviously nutrient is not supposed to be suppressing, it has not suppressed, so therefore you have a complete cancer growth. And doxorubicin is anti-cancer agent, should suppress, but it is not suppressed 100% extent, it is suppressed to some extent, maybe 70-80% or something like that, but still you can see, or maybe 60%, and remaining you can see still here. So if you not done anything else, it should have been this size, and with this core shell almost nothing, with the nutrient it is much bigger even, and with the usual doxorubicin you have still have the tumor. So that means this kind of a magnetization, magnetic nanoparticles can be utilized to suppress these tumors, as demonstrated in this particular the mice example. I hope now you understand how the magnetism and helping in terms of, or magnetic material helping in terms of the cancer therapy. So if you look at the things in the literature, you will find such kind of a magnetic nanoparticles, core shell nanoparticles, mixed core shell nanoparticles, spring joints, all these kinds of things are used in variety of fields, in analysis, food, the security applications, of course huge amount of medical, huge amount of the drug storage, delivery, variety of things, variety in environment applications, everything. So some applications in terms of the carrier and then delivery things are shown here. You can sit and read those kind of things, not a big deal there. Active carriers, passive carriers, catalysts, chelators, remediators, etc., magnetoliposomes, MRI, and single nanoparticle. So variety of, huge variety of applications are possible. This is just a tip of the iceberg, but huge number of different applications are there. So therefore one can use these magnetic nanoparticles, magnetic materials, combined magnetic materials, combined magnetic nanoparticles, etc., for a huge range of applications in this. So with that I would like to say that we have gone through all the basic components of that is required for the magnetism and magnetic materials. Of course if you have, one has to give lectures on this, one can give full course, maybe 2 semesters, maybe more semesters as well, but here we cannot afford that in this particular course. We need to bring relevance just to that application aspects of it, and I guess that I have brought that by giving the basic materials, magnetic types, and then how they are measured, and how they are plotted, and how the magnetization and the magnetization extends, and how such different kinds of magnets can be joined together, hard, soft magnets, core shell magnets, their combinations, and all those things we have looked at. I think more or less we looked at quite a much in this, and we also looked at an example, application example, where we have made that. Look at the this particular thing. Just I wanted to give you a little bit of practice. You can do it also, the practice later. It requires extended practice if you wanted to assimilate the knowledge that we are talking about on this. Let us take one example and look into details, and you can try to work out other queries on your own at leisure by using those basic principles introduced in this course. Itself is sufficient actually. If you have additional knowledge, yes, absolutely great, no problem. So account for the magnetic moment of ET4 and twice, tetraethylammonium twice, NiCl4, that is recorded at 80 and 300 K, and it is 3.25 Bohr magneton at 80 and 3.89 Bohr magneton at 300 K. That's all. So, these observations, how will you understand that? Now, first, so look at this compound. This is a tetraethyl ammonium nitrogen is a 1 plus, is twice 2 plus, that means NiCl4 is 2 minus, NiCl4 2 minus, which means Cl 4 Cls will give 4 minus, that means nickel is 2 plus. Nickel is 2 plus, we know very well, nickel 2 plus is the H system, know that, very simple and easy, and that is where. So, and then if you look at this complex, you have a 4 chloride, that means 4 coordinated, and we know the 4 coordinated kind of things, geometries, what is the kind of geometries that one would expect for 4 coordination is a tetrahedral or a square planar kind. Of course, there are some intermediate geometries, but you do not need to so much worry about it. So, tetrahedral a square planar kind of things with the 4 coordinated complex. And if you look at this, and we know from other studies earlier very well, D8 system is very specialized system. This tends to be converted into if it goes into the square planar kind of a complex, then you would expect 0 magnetic moment. Reason is all the 8 electrons are paired. The reason for that is in the square planar, the gap between the upper orbital versus the lower filled ones is huge. Therefore, as which I explained in the previous class, the low spin high spin comes from this field difference. So, therefore, as a result of that, so that will become. So, since this is not a 0 magnetic moment that you found in this particular example, then it cannot be a square planar, then it is a tetrahedral kind of thing. Okay. So, in the tetrahedral, if you have so you have 2E and 3T2, so you will have 4 and okay. So, that is where you have 8. So, that means you have 2 unpaired electrons, and the 2 unpaired electrons will give you this 2.8. So, this will give mu spin only will give 2.8 Bohr magneton. So, what is found here in this is 3.25 at 80 and 3.89 at 300. So, 3.25 and 3.89 Bohr magneton at 300 K, and this is at 80 K. So, that is basically the liquid nitrogen kind of a temperature. It is much higher than what is expected. So, mu spin only is 2.85 Bohr magneton. So, you can see that the difference, there is an increase at this room temperature as well as at the low temperature. Okay, so this we can try to work out. So, we have already looked at earlier, this kind of thing comes from the spin only, the angular spin plus the orbital contribution, and then the formula also I have given. If you use that formula and work out, so it will give 4.47. So, mu S plus L will give 4.47 Bohr magneton. So, if you have a complete coupling between this spin and orbit, then that means 100% coupling, then you should have got 4.47. But if it is only spin, you could have got 2.85. So, now you can compare with this, and that means there is not a sufficient amount of spin orbit coupling. That means there is a coupling being quenched, the magnetization being quenched. So, therefore, you can find the percentage of quenching, etc. So, that is the reason you can explain. Now, I just give on this very last slide a couple of problems which I would like you to address. There is some information given in the complex. Please try to analyze, look at the number of ligands, bound, charge, oxidation state, and in the bracket given is the Bohr magneton mu effective, and using that you can always try to work out what would be happening. For example, here extra information is given in a solid state. Solid state, you will have these units will join together through the bridging. For example, in this case, the Cl moieties can bridge between the 2 neighbor nickel centers. So, instead of becoming, though there are 4 ligands, it will be a 6 coordinated because of the additional bridging of that. Other things you know very well. So you can try to work out. Identify the transition metal configurations both in octahedral and tetrahedral environments which are expected to have an orbital contribution. I have explained that also in the previous lecture. Those which are having asymmetrically filled T2 or T2G orbitals will only exhibit, otherwise will not. That is expected. Of course, measured could be different. Which one would you expect to have the greater magnetic moment, COCl42 minus and COI42 minus? If you take the only spectrochemical series kind of thing, chloride, iodide, etc., they are expected to have very similar in terms of the weak field kind of a ligands. But the iodide will have a huge amount of covalent character as compared to the chloride. Therefore, the overlap will be greater. So, that will make the transition more possible for the excited state. Therefore, you would have a greater magnetic moment in that too. So, you can try to work out things on this and many more examples I have not given covered in this particular class, but you can pick up many examples to make yourself familiar with this thing. Thank you very much.